Yeah, so we continue chapter 8. So we are doing analysis on tables, the table of counts that is called contingency tables. And the last time that we basically compare the proportions. So we compare proportion to a constant, or we compare two proportions. And this time, generally, we discuss a table which have the two factors. In this example, that we have two factors, the academic performance and the height of students. And in total, we have 30 students in this table, and we have 10 students who are who have good academic performance, and their height is more than 150 centimeters, and so on. And our objective is whether these two factors, the height and academic performance, are related or not. And in a common sense, if we see this table, those two are related because, for example, for the first group, we have 10 out of 20 students have good academic performance. But for the second group with less than 150 centimeters, the 8 out of 10 have good performance. So that is 50% and 80%. So it looks these are significantly different. Or you can also see this table vertically. Out of good students, the 10 out of 18 are more than 150 centimeters. But for poor performance, the 10 out of 12 students are more than 150 centimeters. So these proportions look significantly different. So we want to see this relationship. And the idea is to compare these actual counts with expected counts under independent assumption of two factors. So so this is the last time that we have seen this table. Suppose that these marginal numbers are given. So just we know that how many percentages how many students are, what proportion of students are more than 150 centimeters, and also we know that what proportion of students have a good academic performance. Then given these numbers, we can calculate the expected numbers in the 4 cells. So if the two factors are independent, we should have the same proportion of good students. So maybe 60% of 20 students and 60% of 10 students. So these numbers should be 12 and 6. And also you can fill out this as 8 and 4. And the idea is to compare these two tables. Then we can see how much this actual table deviates from the expected table under independent assumptions. Then we can test the independence between two factors. Yeah, but we want to use the more a larger table to make a general discussion. So now that we think about this table. So this table, the last column and last row are actually the totals. So actually this table is the 3x4. So we are thinking about testing this 3x4 table. So here we say the number of rows as R. So we have 3 rows and number of columns 4. So 3x4 table we want to test. So this is called contingency table. So remember that this is a table for the hair color and eye color of statistics, the graduate students in the Summer University many years ago. And you can see that maybe, for example, the combination of the black hair and the green eyes are relatively rare, maybe in terms of the 25 students who have the green eyes, that only 3 out of 25 has black eyes. But this situation is a little different if the eye color is brown we only have we have as many as 32 students out of 95. So proportion looks much larger. So it sounds like the eye colors and eye color and hair color are related. Okay, so now we calculate the expected table. So we have actual numbers, but based on actual numbers that we can calculate this marginal distribution and this marginal distribution. So in total, the 24% of students have the black hair, I think, and the 61.4% the brown hair, and the 14.6% the red hair. And the eye color, the 40.8% the brown eyes, 30% blue eyes, 80% hazel eyes, and the 10%, maybe 11% green eyes. And based on these marginal probabilities, so these are called marginal because it's the margin of the table. Then, so these probabilities in this table should be the product of these two probabilities. For example, the black hair and the brown eyes, we have to multiply this 40.8% and the 24%. So we get the 9.8%. So that is the product. If these two factors are independent, so this probability should be the product of this and this. This is exactly the definition of independence. So probability factors into products. Then after that, we consider the fact that we have in total 233 students. So we multiply 233 with this percentage, 9.8%. Then we get the 22.8 students. So this is expected number, so it does not have to be an integer. And you can do that for each cell. So these numbers, they should satisfy these marginal counts. So these 95 or 71, 42, 25, 56, 143, and 34 are actually true for the actual table as well. Because we start the assumption that these marginal numbers are correct. I mean, they are given. Yeah, and these numbers, we say these numbers as EIJ. So for example, this is the second row and this is third column. So this one is the E23. And we say actual number as the OIJ, so O23. And we basically think about the difference between E and O, E's and O's. And our test statistic here is take difference between OIJ and EIJ, then take square, then divide it by EIJ, then take summation. So probably taking the difference and taking square, that is pretty natural idea. So when we evaluate the difference between two set of numbers, usually that we take the difference, that is good, and also take square and take summation. That is very common way in statistics. For example, the distance between 2 points are calculated by the sum of the distance in each coordinate square. So that is reasonable. And maybe the one slightly confusing part is divide this by EIJ. So this is basically because of the central limit theorem, but the intuitive explanation is that if sample is small, this difference is large, compared to the sample size. So think about the case that we have expected number equal to 100, and the OIJ is somewhat, if the OIJ determines randomly based on independent assumption, it may be 105 or something like that. But if EIJ is equal to 10, then if we have some randomness, maybe it can be 8 or 12 or something like that. And in terms of difference in absolute value, of course, if expected number is larger, the deviation is likely to be larger. But if we adjust the size of expected numbers, usually this size is larger than this. So this is a common case because larger sample gives somewhat stable the results. So if expectation is 10, sometimes it's 8, sometimes 12, and the difference is just 2. But in terms of percent change, then that is 20% difference, right? But if expected number is large, then usually we don't have that much difference. So it may be 105, it may be 92 or something, but the difference of 20 is a little rare. Yeah, so that is understandable, right? So for example, if you roll a die 6 times, I mean maybe 10 times, then the number of ones, then the expected value is maybe that maybe not very good idea. So okay, so think about a flip a coin 10 times, then count the number of heads. Then the expected probability of head is 50%, we assume. Then our realization may be 4 or 5 or 6, right? But if we have flipped the coin maybe 1,000 times, then probability is 0.5, and the outcome is maybe 500, but maybe 515 or maybe 491 or something like that. And in terms of absolute value, the difference is larger. So we have 9 smaller than 500 and 15 are larger than 500. But in terms of proportion, the difference gets smaller because we have many trials and the results should be somewhat stable. But if n is equal to 10, 4 or 5 or 6, and 4 is just 4%, 40% of 10 times. So that's much smaller than 50%. So if sample size is small, that kind of variation is larger. So basically EIJ adjusts that term. So we take square of OIJ minus EIJ, but we divide this by EIJ. Okay, so it's not EIJ square, but not constant. So this is just the expectation. Yeah, so basically the variation is proportional to, the variance of some random variable is proportional to the inverse of the sample size. So basically we use that fact to justify this EIJ. Okay, so we take the difference between OIJ and EIJ in the first cell, the upper left cell. The actual observation is 32, and the expected number is 22.8. So we take the difference and take square. So that is 9.2 square. Then we divide this by 22.8. And we do this for each term, each pair of IJ. So we have in total the 3 by 4, so 12 terms. Then we calculate this. So this is a kind of measure of discrepancy between actual and observed tables. And we have some theorem. So the statistic, we say this as chi-square. So chi-square. So this statistic that follows the chi-square distribution with degrees of freedom r minus 1 times c minus 1. So in our case, we have the 3 by 4 table. So 3 minus 1 times 4 minus 1 is equal to 6. So this follows the chi-square distribution with df6. And remember that the chi-square distribution with degrees of freedom 6 is, okay, so chi-square random variable with df6 is defined as the same random variables as the square of the sum of 6, the standard normal random numbers. So expectation of chi-square 6 is equal to expectation of this sum of these 6. And z1 to z6 are all normal 0, 1 random variable. So variance is 1 and expectation is 0. So expectation of z1 square is, in this case, the variance of z1. if expectation is 0. So that becomes 1. So we have 6 terms. So this is equal to 6. So chi-square 6 distribution is somewhat like this. So 6 is the mean that is probably slightly larger than the mode. And this is the probability distribution, PDF, of chi-square 6. And if this discrepancy is large enough, then we reject null hypothesis. So if our significance level is 5%, then we take 5% of this, and this is the threshold, the chi-square 1 minus alpha. Then we reject if our test statistic fall in this range. I got one question from Neil. So is chi-square similar to S-square in this case of contingency table? Chi-square is, yeah, in some sense it's similar because the distribution of both are chi-square distribution. That's true. Yeah. Yeah, but I think that we haven't used S-square as the test statistic yet, but here the chi-square is a test statistic. Okay, so I will give you one bonus credit. Okay. Okay, so yeah, so S-square, the sum of square root deviations follows the chi-square distribution. So yeah, and this chi-square statistic also chi-square distribution. So yeah, chi-square distribution is prepared to represent the distribution of sum of squared errors. So yeah, in that sense, it's similar. Yeah, so we reject null hypothesis if this chi-square value is large enough. And our chi-square value was the 13. So that is relatively larger than 6. So we are not exactly sure if it rejects null hypothesis or not, but at least it's somewhat large. So we have somewhat the evidence of dependence between two factors. And this is the so this is the code for chi-square test. This is called chi-square test. Chi-square test. And this is how to implement chi-square test. And the D is contingency table. So this is the 3x4 table, original table. And what we have to do is just type the chi-square dot test of D. So it's very easy. And it reports the degrees of freedom. So this is 4 minus 1 times 3 minus 1. And the chi-square value, it returns the 13.09. And it returns the p-value as well. So in this case, it's less than 0.05. So the H naught is rejected. So the eye color and hair color are dependent or not independent. I got another question from Passer. Why is chi-square test one-sided? Oh, okay, that's a good question. So yeah, so the statistical tests most often rely on the heuristics. So in our situation, the larger chi-square value means the more indication of dependence, right? So to reject independence, basically we reject only if the chi-square value is large enough. So our significance level is 5%. So we have to reject null hypothesis the 5% of the time, even if the H naught is true, but we want to minimize the error, right? So we only want to reject null hypothesis when we have strong evidence of dependence. And here, strong evidence of dependence is larger chi-square value. Yeah, that's a good question. I got another question. So why is there the two commas when selecting the rows and the columns in the first line of code? Two commas. Oh, yeah. Yeah. And that's also a good question. So yeah, you can see here that we have two cameras. And the answer is actually that this hair eye color. So this object is array, three-dimensional array. So actually this data set have two tables. So the first table and second table. And I'm not exactly sure what is the first table and what is the second table, maybe male and female or something. But yeah, so this is, okay, so row and column and page or something like that. Yeah. And this is just first page of this the three-dimensional array. Yeah, you can check the your R session, and this is the default data set in R. So if you just type hair eye color, you will see 2 pages of matrices. That is three-dimensional array. Yeah, and chi-square approximation may not be incorrect. Yeah, this warning message appears because the number of observations are small, so approximation isn't really good. And actually, this warning message appears, I think, that when some cells have number less than 5. So in this case, the green eyes and red hair, we have expected number of 3.6. So that means actual number of observations maybe 2, 3, 4, 5 or something. So it's highly discrete. So of course we cannot approximate by normal distribution very well. So that makes that warning message. So in R, warning message is not an error message. So it's fine as long as you understood the message. Error message means that your code is not correct, so the R cannot run. Yeah, so here, maybe I missed to say, but the number of observations has to be larger than 5. Some people say expected number should be larger than 5. And some people say the observed number should be more than 5. Some people say more than 10 or something. So it's not really an absolute criterion and no magic number, but typically the people think the OIJ should be larger than 5 or expected value should be larger than 5. Yeah, maybe for this lecture that we say OIJ should be larger than 5. That is an easier criterion since usually we only have the data set first. So this criterion can be seen only with checking OIJs. Yeah, that's it. Okay, so the next example, this is very similar example. So the table shows the blood types of 100 Asian Indians and 100 Americans. The numbers are typical for these countries. So the blood type data is interesting. So different countries have totally different proportion of blood types. You can see maybe the type O is common in both countries, but the blood type A is almost twice as common in United States. And blood type B is actually more than 3 times more common than in India than United States. Yeah, in my country, Japan, I think the blood type A have 40%, B 30%, and sorry, the A 40%, O 30%, and the B 20%, and AB 10%. So AB has larger share, and yeah, O has lower share. So it's really interesting. So you can search on the web to see other countries' statistic. Yeah, and we want to test. But yeah, so suppose that we only have 100 observations from each countries, and that we have observed this table, and that we want to test this. So in this case, that we don't really have the data ready in our session, so we have to at first define a matrix. So the first row vector is for India, and the second row vector is for United States. And we do the chi-square test. And here the df is 3. Why? Because we have 4 by 2 table. So 4 by 2, then That means the 4 minus 1 times 2 minus 1. So that is 3. So we have 3 degrees of freedom. Why minus 1? Yeah, maybe I will explain a little bit. So basically, this given this marginal distribution, that we only have 3 degrees of freedom. So that means if we have decided this number and this number and this number, then the other numbers are automatically determined. Because if we know the subtotal, this is automatically determined. And also if we know these subtotals, that these numbers are also automatically determined. So yeah, so we basically have 3 degrees of freedom. So that's the, that does not prove the statement, but that's the intuitive reason that the degrees of freedom is 3. Yeah, so in this case, p-value is very small. So 2 countries have different the blood type distribution, or we can say the country and blood type are not independent. Yeah, so people sometimes say this is the goodness of fit test because we see the difference between 2 countries. But yeah, basically mathematically it's the same as the test for independence. We can either say country and blood type are independent, or we can say the 2 countries have different the blood type distribution. On the latter case, we say that as goodness of fit test. But anyway, so these are mathematically exactly the same chi-square test. Okay, so do you have any questions? Yeah, I think that I think that many people prefer me to explain more examples. So maybe we do that, this one. So we override the yeah. So the exercise 2. Sorry, not sure. Maybe you have to show the screen. So we have okay, so okay, so this is chapter 8, and remember that we have the matriculation data set for Wayne State Medical School, this one. And now we want to test this table, so that is the exercise. So at first, we want to test the smaller table, the U of M and Wayne State only. And the next, we test the entire table for 3 undergraduate institutions. So maybe I want to keep this table in the screen on screen. So maybe okay. So this is our session, and probably you see both. So at first we have to be careful how table that should look like. So we have the 85 enrolled students, and that means the 398 applicants who have not enrolled at Wayne State. So for Wayne State, the U of M. So U of M, the data should be 85 and 398. So applicants are total. So the matriculated and not matriculated, that should be in the table. So first one should be this. Maybe I would say the 483 minus 85. And for Wayne State, that should be 54 and 143 minus 54. And the Michigan State, the 35 and the 266 minus 35. So the matrix should look like this. And if we take the raw total, then that becomes 483 and maybe make it larger, and 143, and the 266. And first, we want to test the difference between two universities, U of M and Wayne State. So we have to take the first two rows. Oh, sorry. This one. So we want to test this table. So we put the chi-square dot test of M1, 2, this. Then we get the result. And actually the p-value is very significant. So U of M and Wayne State have significant difference. And yeah, if the difference is this significant, if we compare 3 universities in total, then of course we will see some difference. But yeah, just we do this also. Then yeah, p-value gets even smaller. And the degrees of freedom is 2 because this is the 3x2 table. And the chi-square statistic is very large, 38.3. So DF2, typically chi-square value is around 2, but this is 38, so it's very extremely large. Yeah, even the first one is extremely large, 24, when expectation is 1. Yeah, any questions? Maybe I have to check the attendance, so maybe I make the participants and just oh, actually, I'm sorry that the last time I forgot to take attendance, so maybe I should give away point for everyone. Okay. 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 Sonali. Okay. So now we go to next section. Just 3 seconds. Yeah, so the next section is the Fisher's exact test. So in chi-square test, our assumption is the all OIJ, the numbers in each cell is larger than 5 or larger. But sometimes we have very small tables, and some people believe that the chi-square test approximation is not good, and it's better to use the combinatorics to calculate more exact probabilities. Actually, some people resist the idea of Fisher's exact test, so it's not clear which test is better, but many people use the Fisher's exact test if the number of observations are small. At least this has foundation for a smaller number of observations in each cell. So the same hypothesis test, so the same null hypothesis, same alternative, but we have the different procedure to test, the different algorithm to test. Yeah, and actually the biggest difference is we don't have any normal approximation. We don't have any chi-square approximation. So we directly calculate the p-value. So that is the difference between chi-square test and Fisher's exact test. So yeah, this is a little abstract, but this test calculates the probability, the P sub T naught of the observed contingency table T naught. T naught is just the matrix, the table, and given the marginal counts and counts for rows and the marginal counts for columns, and the independence assumption. Yeah, and so Fisher's exact test don't use any approximation and any statistical theory for the distribution. So so until now, the all tests uses the some test statistic, either Z statistic or T statistic or F statistic or chi-square statistic. And after that, we calculate p-value. But the Fisher's exact test does not have intermediate statistic and calculate the p-value directly. So that is the biggest difference between this test and the other tests. And yeah, so this test is a little complicated. So I want to have one example first. So suppose that we have some table. And suppose that our observed table is, okay, so maybe, yeah, sorry. Suppose that we have this kind of table. So we have basically the two variables and yeah, maybe I would say that this is row 1, category row 1 and category row 2, column 1 and column 2. Okay. Then suppose that we have some numbers such as maybe the 0, 3, 2, 1. Okay. So this is observed table. Then what we want to do is we consider all possible tables given marginals. Okay, so suppose that this is observed table T naught, and we consider all possible tables given marginals. So what kind of tables are possible? So suppose that this count is 1, then this count should be 2 because the total is 3, and this count is 1 because the column total should be 2, and this number should be 2. And this does not contradict anything. So first row, 3 observations, second row, 3 observations, first column, 2 observations, and second column, 4 observations. And also another possible table is this number is 2. Oh, sorry. Oh, I think that's fine. Okay. So this number is 2, and this number is 1. This is 0, and this is 3. So this is another possible table. I got one question. So it's like playing Sudoku. Yeah. Actually, yeah, if you, yeah. Yeah, it looks like Sudoku. Yeah, and the good thing is, yeah, like Sudoku, if we decide that this cell, actually other things are automatically determined. So 0, 1, and 2. Yeah, I like that comment. So I will give you 1 point. So also in some puzzle games, if we decide the several cells, then other things are automatically determined. In general, if we fill out the cells, which is the number of cells equal to degrees of freedom, then other things are automatically determined. And actually, these 3 are all possible tables. Other tables are not possible. Why? Because if you see the column total, this is 2. So this yellow cell, there should be either 0 or 1 or 2, and no other possible combinations. Okay, then we calculate the likelihood of each table. We say this is T0 and T1 and T2. And for T0, what is possible number of ways to get this table? The possible number of ways to get the T0. Then in total, we have 6 observations, right? So in total, we have 6 observations. So basically, we have 6 factorial ways to assign these observations. So we have A, B, C, D, E, F, or something. So yeah, it's hard to say, but yeah. So and we just the number the elements like you know, that we have first observation have to be here, and the second observation has to be here, third observation has to be here, fourth observation have to be here, fifth and the sixth has to be here or something. So then we have the 6 elements. So for the first choice, we have 6 ways, second choice, we have 5 ways, and so on. So we have 6 factorial ways, 6 times 5 times 4 times 3 times 2 times 1. But to assign that, yeah, but actually if these 3 observations are in the upper right cell, the order does not matter between these first, second, and third choice. So we have to divide this by 3 factorial to get this table. And also in the same way that we have to divide this by 1 factorial and 2 factorial. So yeah, we have 1 observation here, but the 5 and 5th and the 6th observations are in this cell, but the 5th and the 6th are interchangeable. So yeah. So the number of possible you know, realization is only the 6 factorial divided by 3 factorial, 2 factorial, and 1 factorial. And this is in total the 60. So 6 factorial is 720, and this divide by 6, so that is 60. So what's the probability of T naught out of all possible combinations? And that is the 60 over all possible number of combinations. Oh, sorry, then we have to consider how many all possible combinations. So all possible ways to get this marginal distribution. So we ignore these numbers and how many ways to get this table out of 6 observations. Then 6 observations should be the 3 in the first row and 3 in the second row. So that combination is actually the 6 choose 3. And also the 2 observations should be in the first column and 4 observation in the second column. So that means that we have the 6 choose 2 ways to allocate the 6 observations into 2 rows. And the choice of row, the determination of rows and the columns are independent. So we have this 6 choose 2 times the 6 choose 3 number of ways. And this is equal to 6 choose 2 is 15, and 6 choose 3 is 20. So in total, we have 300 ways. So out of these 300 ways, that we have 60 to realize the table T naught. So this probability is actually 0.2. So given these marginals, that we get the 20% probability to get this table T naught. What about 6 choose 4? Yes, the 6 choose 4 is also fine. If you decided to include 2 observations in the first column, that automatically means the 4 observation in the second column. So either 6 choose 2 or 6 choose 4, but we don't really have to do both. Right. And so this probability is 0.2. And you can calculate this probability for other tables as well. So probability for second table, actually probability of second table will appear more often, you can see, because it's more balanced. So it's actually the independent case for rows and columns. So number of ways to get this table is 6 factorial divided by 1 factorial, 1 factorial, 2 factorial, 2 factorial in the same way as the first table T naught. And this is 720 divided by 4. So this is 180. So probability of T1 under yeah, so the probability of T1 if everything is assigned randomly is 180 over 300. So assigned randomly means basically the independently. So this probability is the 60%. And T2, you can do the same thing. So number of ways is equal to the 6 factorial, 2 factorial, 1 factorial, 3 factorial, and it's actually the same as the first one. And the probability of T2 is equal to 0.2. So we get 0.2, 0.6, 0.2. And then the p-value for table 0 is equal to actually the summation of P of t for all t which satisfies less than or equal to P of t0. So P of t0 is 0.2 again. So we add up all numbers which is 0.2 or less. So that is P of t0 plus P of t2. So P value is 0.2. Yeah, maybe I move this to this one. And oh, sorry. Yeah, you can also calculate, for example, the P value for table 1, T1. Then summation of the P of t is less than or equal to PT1, but the PT1 is 0.6. So basically, we add up everything. So this is the P of t0, P of t1, P of, sorry, this one 0.4, right? 0.2 plus 0.2, so 0.4. And the P of t0, P of t1, and a P of t2. So this is the everything, so 1. So often the Fisher's exact test returns the p-value of 1. That means realization is most typical table. So the T0 and the T2 are relatively have lower probability if the observations are randomly assigned, independently assigned. So in this case, the p-value for T0 is 0.4. So anyway, we cannot reject null hypothesis. This is very small table. So this is the way to calculate it. And so in general, that we can calculate the probability of T0 in this way. So possible number of ways, number of combinations given the OIJ divided by all possible combination given the marginal distributions. And the numerator is the n factorial divided by the product of all OIJ factorial. So in the previous page, we have seen that we divided 6 factorial by 1 factorial, 1 factorial, 2 factorial, 2 factorial, or something like that. And that is this part. And the denominator that we calculated the 6 choose 3 and 6 choose 2, but in general, that we can write that in this way. So if you simplify slightly, then we get this. Still, it looks a complicated formula, but basically R calculates this for all possible tables. So that takes a lot of time. So it can apply for smaller tables. So that is the Fisher's exact test. And I got a question. So could we simplify the formula with multinomial coefficients? I don't know. I believe that this is the simplest form, but I don't think it can. Yeah, I think this is the simplest expression if we think about the general case. So if we have a specific case, canceling the factorials are important for computer science, right? So if RJs are very large and the n is also large, we have to cancel it so that it does not explode or it does not become 0. But I think in terms of mathematical expression, this is simple enough. Computationally, maybe we have more trick we need. But that's a good question. And as we have seen in the previous example, this is the p-value. So we add up all probabilities, which is the less than or equal to that table. So that is basically, the definition of p-value, right? So the definition of p-value is the probability of more extreme event happens under null hypothesis. So exactly it follows that definition. What time? Okay. So, and this is the sample code. We have exactly the same format as chi-square.test, chi-sq.test. So we have the Fisher.test function. And yeah, we only have p-value as the output because we do not have intermediate products such as degrees of freedom or chi-square distribution. Could we, I got another, yeah, so that's it. Sorry. So the chi-square distribution, we got this test statistic, and from Fisher, the exact test, we got this p-value, and these are similar because the number of observations are reasonably large for those tables. The smallest one is 3.6 as expected value, and the largest one is like 50. Yeah, so that's it for this section. And exercise 4, do Fisher's exact test and the chi-square test for 2x2 table and compare the results and how to interpret the obtained p-value for Fisher's exact test. And the exercise 5, do Fisher's exact test for example 4, blood type of 2 countries. Yeah, I think that these are really similar ones. So I will do exercise 5 only. But okay, so we got maybe I got one question. So in what real life application would Fisher exact test be useful if it can only take small samples? Yeah, that's a good question. So in my experience, I was developing the business survey, and basically the survey wants to make sure that all kind of companies are selected in a good balance. So basically that we have like in terms of capital size, in terms of the number of employees, we have the large population and the small population and something like that. And we have some table. And so these numbers are somewhat large, like, okay, so 20, and yeah, so yeah, maybe this is like the 8 or something, and this is like the 120 or something. And sometimes some cells are really small, like 2. So the very small capital, but the large number of employees. So that is very uncommon. So we have some small number. So in such a case, we cannot really use the chi-square test reliably. So most cases are fine, but some cases have a very small number. So in this case, we want to do Fisher's exact test. And also sometimes entire numbers are really small. Like we only have for example, this business survey is for very minor industry and total number of companies is just 10 or something like that. Then we still want to see if the yeah, sorry. I think that this question is a little more, this problem is a little more complicated setting, but yeah, anyway, so the table is sometimes small, but still we want to test. That happens in some situations. Sorry, maybe this isn't really the best example to explain. I got another question. In what situation might you want to avoid Fisher's exact test? The sample is too large. So every observations are large, then we have no benefit. So it's fine to use it, but it takes large amount of time, so computer resources. So if sample size is too large, that's not good. Okay, so now we do this example again. Yeah. So now again that we do the exercise, and yeah, maybe we should do both. Or yeah, first maybe that we do exercise maybe 5. Exercise 5, 2 countries. So we have data for 2 countries. So the blood type data for the India is, we have some numbers, 38 and 23 and the 32 and 7. And the United States that we have 44 and 42 and 10 and 4. So I think this is the case that the we wonder we should use chi-square test or Fisher's exact test. Just one cell is slightly smaller than 5. And chi-square test result, it's very significant. And Fisher test, and we got this. And yeah, actually even these are both very small. These numbers are pretty similar. So 0.00037 and 26. So both are highly significant, and we don't have any trouble. And in this case, probably Fisher's exact test isn't very useful. So just we can use chi-square test. Maybe we have 4, so maybe some people still want to use this. But and the first yeah, and also we would like to do, I would like to do exercise 4 as well. And 2125, that is our table. So exercise 4 and the 2125. So 2125. So our table is here. Then Fisher, so this table is very small, so we should do Fisher's exact test, and it returns p-value equal to 0.5. How about chi-square? We get the 0.67. Anyway, so this is not significant at all, so it doesn't really matter. But yeah, in some cases, it's certainly on the boundary, like the 0.1 or 0.05. So in this case, I recommend you to use Fisher's exact test. Okay, so that's it for chapter 8. Yeah, so some statisticians object to Fisher's exact test. Yeah. So probably that's because the way to calculate the maybe p-value, I don't know why they object, but under some situation, the Fisher's exact test doesn't work well. So some people claim that, but that is very, the high-level academic topic, and I think that no practitioners complain about that, and probably you don't really have to worry about it. But yeah, in some simulation studies, it supports the chi-square test more than Fisher's exact test, even if approximation is not good. I'm not exactly sure about the reason behind it. Sorry. Yep. Yeah, so basically they do simulation based on interdependent assumption, and the chi-square distribution gives more accurate p-value than Fisher's exact test. Some people obtained that result I have heard of. Yeah, even without any data set for final project, if you do such theoretical, investigation, certainly you can get you can make very good presentation. So usually I recommend you to do some the applied the data analysis, but if you are interested in that kind of thing, can be done. And sorry, and we go to chapter 11. Chapter 11 slides are available on the website. And the chapter 11, we have the multiple linear regression. So I think I have shared screen, no? Maybe no. Okay. And today I want to discuss just how to present data for multivariate case. So suppose that we have several variables. So I have the property sales, property sales data set. So this data set includes the price of houses and the square footage of houses and the year and the number of bedrooms and the number of bathrooms. So we have 5 variables in this data set. And we want to see the relationship between each pair of variables. Then we can use the pairs function to make all scatter plot. Yeah, this is a little bit inefficient because this graph and this graph basically have the same information. But if we have, okay, so multiple variables, basically we have the scatter plot for each pair. So yeah, a slight difference is, for this graph, the horizontal axis is square footage, and the vertical axis is price. And this one, actually the vertical axis is square footage, and the horizontal axis is price. So slightly different, but these are flipped graph each other. And you can see we have some relationship between these two variables. Slightly violates maybe linear relationship. Certainly we have some pattern, and yeah, and still we have positive pattern between price and any of these 4 variables. So sometimes this is useful to make. Maybe if you put more than 10 variables, maybe the each scatter plot becomes too small. Yeah, we have some trouble for this graph, the number of bedrooms and the number of bathrooms. These are actually the discrete data. So the number of bedrooms in this data set is either 0 or 2 or 3 or 5 or 6. 0 or 2, 3, 4, 5, 6. Yeah. And the number of bathrooms either 1, 2, 3, or 4. So this point represents many observations probably. So we cannot really see the tendency. So that is a problem. But but I think it's good to make this because it can be made only with a few seconds. So this may be useful in your final project if you want to see all pairwise the characteristics. And another way to present the relationship between variables is this correlation plot. The date isn't really very useful information here, but including the date, we have the 6 variables: date, price, square footage, and we calculate the relationship between each pair of variables. Price and the square footage has very high correlation of 0.89. Price and price, of course, correlation is 1. So diagonals are all 1s. But the other things that we have some positive, some negative correlations. And we can plot this in a graphical way by using the CORR plot function. So, okay, so these data frames, so correlation matrix can be obtained by just COR of D. But if you put this COR of D in this plot, then we can make this matrix. And it's somewhat, kind of convenient because we can immediately see the level of the correlation. So this bar explains the scale. So actually the most variables have positive correlation, but the particularly the price and the square footage have a higher correlation. Price and the number of bedrooms have lower correlation. And maybe the number of bedrooms and the number of bathrooms, the maybe even lower correlation. Or year and the number of beds. Year and number of beds don't have any, the logical relationship. So that sounds reasonable that we have small correlation. Yeah, so this is useful that when you start to look at the data competition, usually people at first see this kind of things. And I think you have some options. For example, the size of the circle replaced by numbers or something like that. So we have several options to make this graph. You can check the correlation.corr plot function to see it. I think this is in default package. Maybe not. This is, yeah, you can search on the website to see. I think this is in the CORR plot package. So this is in CORR plot package. So the package name and the function names are the same. So COR plot package, you have to leave. Oh yeah, actually here, yeah, library CORR plot. Yeah, and the next one is the response versus all predictors. So in many of the final project, you set some objective. You want to see how y is explained by other variables. And you have possible predictors, x1, x2, x3, and x4. In our example, maybe the year built or a square footage or a number of bedrooms and number of bathrooms. And sometimes it's convenient to make response versus each predictor. Especially if we have many possible predictors, the pairwise plot is not really informative. That we are not really looking into the relationship between the bedrooms and the bathrooms, but we want to see relationship between price and other variables. So in this case, we can use this plot. So this is from the ggplot package, and it can automatically generate these figures. And that can be done by the ggplot library and also the reshape library, and we put this. So ggplot is more comprehensive function to make plots. So this is data set, so DM, and we have some codes, so that we have some the change of format in D. And then the aesthetic option, so we have to specify the features, specifications of the graphs. In this case, the X is the value of predictors and Y is price. And then we get the facet wrap function, and then the tilde, the variables, a variable, and the scale is equal to 3. So this is just you can see this is just the one set of code. Then this means the scatter plot. And actually, you connect this with the plus sign. So basically, the ggplot is one function, and the plus some other options further specify what graphs that you want to make. Then we get this plot. I got some questions. First question, what does AES, aesthetics? I don't know why we say aesthetics, but why? But this just is specification of graphs. In the last line of code, the same in most scenarios, last line of code. Yeah, it's the same as long as you want to make the response versus all predictors. The scales free. So that means we have different scales for these. Actually, sorry, these are the same, but yeah. maybe the predictors, right? Yeah, but mostly the same, especially if you are making a scatter plot, that we always the geom underbar point. So if we want to make histogram, we have some different code and so on. We have the ggplot, the textbook named ggplot. Then you can see more details about how to use this ggplot function. Okay, so it's already 55. Yeah, and sorry, I would like to finish just last one. So this is the graph for the number of bathrooms and the number of bedrooms. And the problem is that we have so many points at the same location. So many houses have 3 bedrooms and 2 bathrooms. But still, we want to see we want to reflect the information that we have many observations here. And our strategy is to give some noise. So even though this should be exactly at 3.2, that we add artificial noise so that we can see there are many observations here. So that is called the jitter plot. So basically the jitter function add some artificial noise on this vector and also this vector. Then you can plot. Then we can make this. Then you can see the most observations are around here. So that is more informative than just usual scatter plot. It's noise, yeah. Yeah, so that's it for today. So yeah, next time we discuss the multiple linear regression. So that's it for today. So if you don't have any questions, see you on next week.